All right. Well, let's finish up this section. Last time we started with talking about the intermediate value theorem. So the idea behind the intermediate value theorem was if you have a point below the x-axis and you have a point above the x-axis, and I want to connect the dot down here to the dot up here without lifting my pencil, what's going to happen? It has to cross the x-axis somewhere, right? Okay. We're going to use that here in a minute for solving inequalities. But let's do one more problem like we ended class last time. This one says to show that the function has a zero between 0 and 1. It looks ugly. That looks like a really ugly function to start with, right? It's not asking us to find it. It's just asking us to show that there is one, right? So again, we're going to use that same idea. We want to show that it's below the x-axis at one point, and it's above the x-axis at the other point. Okay? So what do I need to do to start with this? Plug in 0 and plug in 1. Plugging in 0 is pretty straightforward. What do you get when you plug in 0? 420, right? Because we plug in 0, all the x's go away, doesn't it? That's positive, certainly. Right? 420 is bigger than 0. So even before we plug in 1, what better it turn out to be if we want to find if we're going to argue that there is a 0 between it? It better be negative, right? It has to switch signs, correct? Okay. So what do you get when you plug in 1? It's a good question. Good. Okay. Notice that 1 to any power is going to be what here? 1. So I'll get 8 minus 68. That's negative 60. Plus 160. That'll give me 100. 182. What is that? 470. And then plus 420. It'd be negative 470 plus 420. And I'll get negative 50, I think, when I'm done. Yep. Good. Which is less than 0. Okay. So again, the idea here is now that since f of 0 and f of 1 have opposite signs, that's the important part. There must be a value, must be a 0 between those two inputs, 0 and 1. Your function has to be continuous in order to be able to argue this. And again, continuous means, just intuitively, continuous means that I can draw the graph without lifting my pencil. Is that okay? So again, if you're asked to show that something has a 0, and you're always going to be asked if a polynomial has a 0. So polynomials are always continuous. You plug in the endpoints and show that they have opposite signs. That's the big deal. Questions on that one, Will? All right. So where does this apply to the other type of problems that we're going to solve in this section? So in this section, the title of the section is your polynomial and rational inequalities. This is a polynomial. It's factored for us, right? Okay. It's factored for us nicely. We've done problems like this. But instead of saying it's equal to 0 and finding the zeros, this one's saying when is it greater than or equal to 0? Well, our first step in solving these is going to be figure out where it is equal to 0. Okay? So we have x plus 5 squared times x minus 1 times x minus 4 equals 0. Let's do that first. When does that happen? We did this on the last exam, right? When's this equal to 0? What makes this part equal to 0? And what makes this one? 1, and this one? 4. Good. Now, if we were to graph this, these are the points at which the graph hits the x-axis, and these are the only points where the function hits the x-axis, right? The graph hits the x-axis. Those are the zeros, right? Doesn't cross somewhere in between. We found all of them. That's all of it. Okay. All right. So that's we're going to use that idea and with the intermediate value theorem. So what we're going to do is we're going to set up a table. Okay. So my table here, I'm going to use an interval. I'm going to have a test point. And I'm going to have a sign of the function. Okay. So let me tell you how we're going to make our intervals. Okay. We found the 3 zeros, didn't we? And let's think about it from a number line standpoint. I'll draw it off to the side. If I have zeros at -5 and at 1 and at 4, how many different intervals do you see that are those 3 points divided the real number line into? 4, right? I've got this interval, this one, and that one, right? Okay. So I want to write those 4 intervals down. The first one is -∞ to -5. The next one would be -5 to 1, 1 to 4, 4 to infinity. Okay. These places where, if you think about the graph, these places where the graph hits the x-axis divides things up into 4 pieces. Okay. Now, what do I mean by test point? Okay. Well, remember, these are the only points at which the function can actually touch the x-axis or cross the x-axis, right? Those are the only zeros. So what I mean by that is, just think from you don't have to draw this picture, but if I'm over here at -5 and I hit the x-axis at -5, if I'm above the x-axis over here, can I also be below the x-axis on that same side of -5? Because again, intermediate value theorem says what? If you're above at one point and below at another, what had to happen in between? Cross it. Do we cross over there at all? No, we only cross at -5, 1, and 4, right? Those are the only places. So what we mean by a test point is if I plug one point in to the function and it's positive, then it's positive that entire interval. Okay? Or likewise, if it's negative on the entire interval. Okay? You get to choose whatever you want as long as it's in the interval. So pick something less than -5. -6. Good. Okay? You could use -6, -7, -10 billion and 3, whatever you want to do. It's pi day, so you could do -2 pi if you wanted to. It's March 14th. It's pi day. Okay. All right. So now what we're going to do is we're going to plug the -6 into the function. All we care about is whether it is positive or if it's negative. That's all we care about. We don't care about the value. Just is it above the x-axis or is it below the x-axis? Okay. But if I plug it in, we'll have -6 plus 5 squared, -6 minus 1, -6 minus 4, right? This first piece that I'm underlining, is that positive or negative? No, what I circled in red. What is it? That's squared, right? It's always positive, isn't it? All right? So we have positive times, this piece is negative times, this piece is negative. So what is the answer going to be? It's going to be a positive, right? We agree? Okay. Do the same thing for the next one. We want a test point between -5 and 1. Negative 2 works. I always like to choose 0 if I can, because 0 is always a good one to do, right? It's always easy. But you can use whatever you want. It doesn't matter. But since 0 is in there, I'm going to use 0 because it's an easy number to plug in. What do you get? I'm plugging it. Again, we're plugging it in here. I'd have... You don't have to write these parts out all the time, by the way, because all we care about is the sign of it, whether it's positive or negative. The first part is positive. The next part is negative. The next part is, and again, we get positive. Okay. Pick something between 1 and 4. 3. That works. Now, rather than actually plugging it in, let's see if we can figure it out. If I plug in 3, the first factor is going to be positive. The second factor will be positive, and the third factor will be negative. When you multiply, you get negative. Finally, the last one, 6, sure. What do you get for all your factors in that case? Positive or negative? They're all positive, right? If you need to plug the numbers in, please do, but it's not necessary, because again, all we really care about is it positive or is it negative? Okay. All right, so again, just to emphasize what the intermediate value theorem says, we know that the only places where the function can cross the x-axis is at negative 5, 1, and 4. That's it. We found the zeros. That's the only places where it can cross, right? What happened at negative 6? At negative 6, the graph is above the x-axis. So that means on the entire interval, the graph has to be above the x-axis. Okay? Likewise here, at 0 it was above the x-axis, so everywhere in that interval has to be above the x-axis. Everywhere in this interval has to be below. Everywhere in this interval has to be above. That's what that means. Okay? So those are the only places where we can possibly have it switch signs. All right? Now let's look at the original problem. The original problem wasn't an equation. The original problem is an inequality. Which of those do you think we care about? The positives or the negatives? Why do you think so? You're right. Why is it the positives? Because the negatives would be less than 0. It says greater than or equal to 0, right? So what intervals do you think we're interested in? Okay, yep, negative infinity to a negative 5, negative 5 to 1, 4 to infinity. Now we have to be a little bit careful the way we write it. Notice this is going to be included, right? It's equal to. Okay, so when we write our solution, we'll do negative infinity up to negative 5. We also have negative 5 to 1. And we have 4 to infinity. Now notice, this is a perfectly fine way to write it. Can you combine those two together, though? Yeah, it's negative infinity to 1. Yeah, I can combine those together since there's an overlap at negative 5, right? Okay. So this would be, I could also write it as negative infinity to 1 union 4 to infinity. That's because it's equal to. If it weren't equal to, I would have parentheses around each of those, and I would not include I wouldn't be able to rewrite it this way. All right, what questions do you have on this one? Okay, let's do the next one here real quick. Notice that in the previous example, everything was already factored for us, right? And we also set it equal to 0 because that was how we figured out the zeros. Is this factored? Not a trick question. Is this factored? No. Is it 0 on one side? No. You have to do that first. You have to get everything on one side, and you have to factor it. Okay? It's important. You have to put everything on one side, just put 0 on the other, and you got to factor it. Okay? Okay? That's step 1. All right? So let's move everything over to the left. We'll get 3x cubed minus 6x squared minus 12x plus 24. The only real good technique that we have for factoring 4-termed polynomials is to group, right? Group the first 2 pieces together, group the second 2 pieces together. What can you factor out of the first 2? Okay. When you factor out of the 3x squared, you get x minus 2. Now, again, when you factor by grouping, I need to see that in the next piece as well, right? Because I want to factor that out as a common factor. So what do we need to factor out of the second 2 terms to make sure that I see x minus 2? I got to factor out a negative 12, right? When we factor out the x minus 2, what are we left with? Okay. Now we need to factor a little bit more. I could have done this first, but do you see a common factor? A 3? Let's go ahead and pull it out to the front. When you pull the 3 out, I could have done that first, right? Because everything had a 3 in it to start with. Okay. When we pull a 3 out in front, what are you left with in the parentheses? X squared minus 4. And how does that factor? Good. So that's the difference of 2 squares, right? Now we have everything factored. I'm going to clean it up a little bit. Since I have an x minus 2 here and an x minus 2 here, I can write it as x minus 2 squared. Again, first step is to factor. Are we okay with the factoring? Okay? Wasn't too bad. All right. That's first. I've got to get everything on one side and factor. Now we're going to do it just like we did the previous problem. Okay? I first need to figure out when is the function equal to 0. What are the zeros for that function? Good. The zeros here are x equal to negative 2 and positive 2. We have 2 zeros, so how many intervals are we going to set up? We have 3, right? Okay, so we'll have 3 intervals. What are the 3 intervals? Okay. Okay. Good. All right, now we'll pick some test points and get the signs. What's a good test point for your first interval? Negative 3. Now again, it's a lot easier to plug this into the factored form. Right? It's a lot easier to plug it in here. Agreed? Okay. All we care about is if it's positive or if it's negative. Okay. If you need to write it out, fine. If you need to put in your calculator, that's fine. But we really just care about is it positive or negative. When you put in negative 3 into the first factor, what do you get? Negative. the second factor is always positive, right? So negative times positive gives you negative, right? It's a negative sign there. Pick a test point between -2 and 2. 0. First factor is positive, and the second factor, since it's squared, is always positive. Positive times positive is positive. Again, if you need to write it out, please write it out. That's okay. If you need to put it in your calculator, put it in your calculator. That's okay. But all we care about is it positive or negative? We don't care about anything else. Okay. Test point between from 2 to infinity. What do you want to use? Sorry, I didn't hear you. 4. Okay. Put in a 4. The first factor is positive. Second factor is also positive. So the whole thing is positive. So far, so good? What do we want to look for in this case? The positives or the negatives? The negatives. So which interval are we talking about? Okay. So your solution here is negative infinity to -2. Do we want to include the -2 in this one? No, because why?
It's not equal.
Good. Notice in this case it's a strict inequality, right? There's no equal to, so that'll be a parenthesis. Okay. That's how we know if we're going to put a parenthesis or not. Okay. I know that I put parentheses here, but I'm going to emphasize with those parentheses that I want to pick a test point in the interval, right? I don't want to pick the end point. Okay? Okay, so let's, pardon me, let's switch over to rational inequalities. What we've done here is polynomial inequalities. Switch gears a little bit, do rational ones. We just talked about rational functions in the previous section. Remember your rational functions, the root word is what again for rational? Ratio, right? It's a fraction. Top and bottom are polynomials. That's what a rational function is. Okay? All right. So remember our intermediate value theorem. The important part for our intermediate value theorem is that if f is continuous on the interval from a to b, then, and I should say and, if f of a and f of b have opposite signs, then there's a value c between a and b, such that f of c is equal to 0. Okay. But what did I underline in that statement? Continuous. Whoops, I forgot a letter. Continuous. Sorry. It's continuous function. When we did our graphs of rational functions, were rational functions always continuous no matter what? Or did we have some places where we had to pick up our pencil? We had some pencil picking up problems, didn't we? Where do we have to pick up our pencil in particular? We had to pick them up at the asymptotes, right? The asymptote, even though we put that little helping line in there, that asymptote's not part of the graph, right? So if you've got a rational function with a vertical asymptote, you might have something that goes like that. I have to lift my pencil, go to the other side, and continue on my graph, right? Agree? So for rational functions, when we do rational inequalities, not only do we have to worry about the zeros, we also have to worry about these breaks. Because did my function switch sign here? When I went across the asymptote, did it switch sign? Did it go from positive to negative here? Yeah, sure did, right? Did I cross the x-axis from here to here? Well, did I hit the x-axis, I should say. Did my function hit the x-axis between here and here? We did over there, but not between here and here, right? Okay. So not only do I have to check out where it crosses the x-axis, I also have to check out the asymptotes for irrational functions. That's the big deal, okay? So for rational functions, the idea here is the function's not always continuous. Okay? And I can't spell continuous this morning, apparently. The function's not always continuous, so we also have to check where there are asymptotes. Okay? I have to be careful. Going back to when you solved rational equations, like for example, I'm going to write this on the board. You don't have to write it on your paper. If you had 1 over x plus 1 minus 1 over x minus 3 equals, say, 2, when you solved equations like that before, what was your first step? What did you do first? What don't you like about that equation? It's fractions. So what did you do first? Yeah, you multiply by the denominators, right? You got rid of the fractions, didn't you? That was your first step when you solve those types of equations, right? I don't like this x plus 1 in the denominator, so I'm going to multiply both sides by x plus 1. I don't like this x minus 3 in the denominator, so I'm going to multiply by x minus 3 and get rid of them, right? Guess what? That's exactly the wrong thing to do for inequalities. Okay? Let's think about why. Why do we not want to multiply an inequality by a variable? Think about when you multiply both sides of an equation by, or excuse me, both sides of an inequality by a number. Does it matter if that number is positive or negative? When you multiply both sides of an inequality by a number, does it matter if it's positive or negative? Yeah, right? If it's positive, do you flip the inequality or keep it the same? Keep it the same. But if it's negative, you flip it. If it's a variable, do you know if it's positive or negative? No. So I don't know whether or not to flip the inequality. Okay? So that's the important part with this. What do we not want to do? We do not clear the denominators. Okay? Very, very important that you do not clear the denominators. Okay? Again, the reason for that is because you're going to be trying to multiply by variables. You will not know whether or not to flip the inequality. Okay? I know it's tempting. I know you hate those dirty little 8-letter F words, right? Hate the word fraction, right? You want to get rid of them. Okay? But you can't for rational inequalities. You literally cannot do it. Okay? You just have to deal with it. You'll have to deal with the fractions. I'm sorry. I wish I could tell you something better. All right? All right, so how do we attack these instead? Same idea that we did with polynomials. Luckily, it's the same concept. Get 0 on one side, factor everything you can. Okay? Same concept, right? Isn't that what we did for rational functions anyway? I told you the first thing you do is factor the top and factor the bottom, right? So you can tell where the x-intercepts are and tell where the asymptotes are. That's why I told you to do that first. Because what we care about are x-intercepts and asymptotes in these problems. Okay? All right, so let's look at this one. Notice it's already set up with 0 on one side. Don't have to do anything there. Is there anything to factor on the left-hand side? Do we need to factor x minus 5 or x plus 2? No. We're already set up good. All right. So your first step here is, just like what we talked about for rational functions, we're going to find the zeros, the x-intercepts, and we'll find the asymptotes, the vertical asymptotes. Okay, that's your first step. Now, just like what we talked about in the previous section, zeros, x-intercepts, what did you look for the x-intercepts? What did you look at the top or the bottom for x-intercepts? Top, right? What did you look for asymptotes? Bottom, yeah. What makes the top 0? 5. So for your zeros here, x equals 5. For your asymptotes, what makes the bottom 0? -2. Good. Notice that just like for your polynomial inequality, your first step is finding zeros. We're just finding zeros on the top and finding zeros on the bottom. Okay? Still the very first step that we do. Okay? Pardon me. What was the next thing we did for polynomials, inequalities in the previous ones? We made that intervals, right? Okay. These are the two numbers that we need to worry about. The x equal to 5 and the x equal to -2. Those are the two numbers that you need to worry about. All right? I'm just tired of this thing doing this to me today. I forgot to do that first. Those are the two numbers you need to worry about, right? The 5 and the -2. Because why? Let's look at this picture that I drew on the board. Did I switch sign when I went from this side to this side? Did the sign switch? Yes. So we can switch signs at an asymptote. Did we switch signs at a 0? Yeah. It switched signs here too, didn't it? Okay. So at zeros and at asymptotes, that's where we can change sign, and that's what we're interested in. Okay. So we've got two places where we can switch sign. I'll write this down. These are the numbers where the function can switch sign. So how many intervals are we worried about now? How many intervals are we worried about? I think so. If we think about putting these on a number line, I got -2 and 5. So I got 3, right? I got that one, that one, and that one. Agree? Okay. All right. So the first interval will be, and the second one will be, and the third one will be I to infinity. Do our test points here. What's a good test point for the first interval? Ooh, for the first one? I need to be less than -2. -1 works okay for the second one, right? About the first one. -4, sure. And the last one? 6. Again, it doesn't matter as long as you're in the interval. Now we want to plug these into the function, right? Again, I'm going to write it out longhand here to start with, but again, all we care about is it positive or is it negative? Okay? All right? That's all we care about. Okay, first one we would have -4 minus 5 over -4 plus 2. The top is, and the bottom is negative. Negative divided by negative is positive. Okay? Again, if you need to put in a calculator, that's fine, but all we care about, literally, all we care about is it positive or negative? Put in -1. The top is, and the bottom is positive. Negative divided by positive is negative. The last one, what do we get? Yeah, it'd be positive the whole time, isn't it? Okay. What are we looking for? Positives or negatives? The positives. So what intervals are we talking about? Okay. Now notice I didn't put a grouping symbol on those yet. This one you actually have to pay attention to. Okay. In the previous examples that we did, when we had an equal to sign, what did you put on your endpoints? If we had an equal to sign, did you put a parenthesis or a bracket? Bracket. Putting bracket on both of these is wrong. Okay? A bracket only goes on one of them. Which one does the bracket go on? The -2 or the 5? Why is it the 5 and not the -2? What's bad about -2? What does -2 do to the function? It puts a 0 in the denominator, right? We cannot put a negative, or we cannot include the -2 because it makes the denominator 0. That's a bad number, right? So this one has to be a parenthesis, but this one is a bracket. Okay. You have to be careful. You never, ever, ever put a bracket where you have an asymptote. Okay. Even if it says equal to, you never ever put a bracket on an asymptote. Okay? It only goes on where the top is 0 and if you have an equal to sign. Okay? If it's strict inequality, they're always parentheses. Okay. What questions do you have on that one? Okay. Work on the next one for a minute and then we'll chat about it. Your first step on your next one will be factor, by the way. Factor top, factor bottom. Let's go ahead and chat about it, just because of more time than anything. Okay. All right, did everybody get the top and bottom factored like that? We okay with the factoring? Are we okay with the zeros and the asymptotes? Those parts okay? So remember again, when we make our intervals, we want to put our numbers in order essentially, right? So -6, 1, 4, 5. That's going to divide us up into 5 intervals. We've got the piece that's less than -6, between -6 and 1, between 1 and 4, 4 and 5, 5 and infinity. That part okay? You happy with those? Test points, you might have different test points. This is the ones I picked. Doesn't matter what you pick. As long as you pick something in an interval, you're good. Okay? Those just happen to be the one I picked. Now I went ahead and put the signs in there, but if we put in -7, how did I know this was positive if you put in -7? What's every single factor if I put in -7? They're all negative, right? Negative times negative on top makes positive. Negative times negative on bottom also makes positive, so we get positive overall. If we put in 0, or whatever test point you decided to do for this interval, which sign flips? Which one's no longer negative and is now positive? Which of the 4 factors is now positive? The x plus 6 is now, right? When you put in 0, that one's positive. The rest are still negative. So you end up with a negative. Which one's the next one that flips? The x minus 1 does, right? Those 2 are positive. These 2 are now negative. We get positive again, don't we? And then you should be able to check the other 2 are going to be negative and positive. Is that okay for checking? Okay. What are we looking for? According to the problem, what are we looking for? The positives or the negatives? The negatives. So for our solution, what would we get? Okay. And notice they're all going to be parentheses here because why? It's a strict inequality, right? There's no equal. We agree? Okay. If it had been equal, rather than just a strict inequality, had it been equal, where would you have put brackets? The -6 and the 5, you would never put it on the 1 and the 4 because those are asymptotes. Okay? All right. I want to just start the next one. We won't finish it just because of time here. But are we okay with that one? All right. Now, at the beginning of all of this, I told you that you want to approach these like you do the polynomials, right? You want to get 0 on one side, correct? Okay. So to do that, I need to move one of them to the other side, correct? Okay. So I'll just move the 2 over x minus 5 to the left. I also told you 2 other things. I told you factor everything that you see. And I also said never, ever, 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 ever multiply both sides by a variable. Right? Okay. But right now I don't see how to factor anything necessarily because why? It's not a single fraction like these were, correct? So on these, I'm going to have to get a common denominator, right? And combine them, okay? I don't have any other choice. I know it's terrible, okay? But I don't have any other choice. I have to get a common denominator and make a single fraction. You don't have a choice, okay? To get a common denominator, oops, I forgot my plus there. What do I need to multiply the first fraction by to make a common denominator? X minus 5, and the second one we need to multiply by x plus 1. Okay, good. So I'll take our 3 over x plus 1 times x minus 5 over x minus 5. And we'll take our 2 over x minus 5 and multiply by x plus 1 over x plus 1. Now we can combine I don't need to multiply out the denominator. I want it factored anyway. Leave it as x plus 1 times x minus 5. On top, we'll have 3 times x minus 5 minus 2 times x plus 1. Just going across the top there, right? Now I will simplify the numerator. So distribute your 3 through, you'll get 3x minus 15. Distribute your negative 2 through, so you'll get negative 2x minus 2. And then finally, I will get an x minus 17 on top, and then over x plus 1 over x minus 5. Does that now look better? This looks exactly like what you were just doing, doesn't it? Okay. Yeah. All right. So I'll leave that there. But moral of the story, if you've got two things that are apart like this, you're going to have to combine them using a common denominator. Okay. Have a good break, everyone. If you're traveling, be safe, please. I want to see everybody back in one piece in a week and a half. Okay. All right.